This lesson reviews complex numbers and basic operations with complex numbers. We're first going to talk about the powers of I. Remember, I represents the imaginary number, which is the square root of -1. But we can treat all of the rules of exponents apply to the imaginary number I, just like it applies to any other number. So if we want to look at the powers of I to the 0, well, anything to the 0 at power is going to be just the number 1. So I to the 0 is 1. I to the first is going to be I again. I squared is what you get when you multiply the square root of -1 times the square root of -1. So that turns out to be -1. And then I cubed is -1 times I. So it's -I. Once you get there, if you go to I to the fourth, that's the same as I to the 0, and the cycle repeats. So anytime you raise the imaginary number I to an exponent, you're going to get one of 4 answers. So there's an efficient way to do this. Let's say if I want to raise I to the 27th power. There's an efficient process to do this to evaluate, because we only have one of 4 answers that it's going to be. So to evaluate I to any exponent, you're going to divide the exponent by 4. And then look at the remainder. And it's going to follow the same pattern that we just did. When the remainder is 0, when the exponent is divisible by 4, that means I to the n is equivalent to raising I to the 0 power. So any exponent that's divisible by 4, that's going to simplify to the number 1. When the remainder is 1, that's equivalent to I to the first, so my answer is going to be I. When the remainder is 2, that's equivalent to I squared, so that's going to be -1. And when the remainder is 3, that's equivalent to I cubed, and that answer is going to be -I. So the remainder is equivalent to the simplified exponent. And again, you're going to get one of these 4 answers. So for example, if I want to evaluate I to the 35th power, I take 35, I divide it by 4, and that's 8, and that has a remainder of 3. Well, this is what I'm looking for. So that's equivalent to I cubed. That turns out to be -I. So I to the 35th power is the same as -I. So a complex number is composed of a real and an imaginary part. It's not always just completely imaginary. So here's the standard form that we use. And sometimes we have, we represent a complex number by the letter Z. But Z is equal to A plus BI. So when A is 0, the number is purely imaginary. So everything is I. And when B is 0, then the number is real. So we have, instead of the standard Cartesian plane where everything is in the reals, we have an imaginary plane where the x-axis are the reals and the y-axis are the imaginary numbers. So this value Z are points in the imaginary plane, where A is the x values and B is the y values. So that you've done last year. I think you also drew a vector to the point. I just wanted to demonstrate that imaginary numbers can be graphed in the imaginary plane, just like real numbers can be graphed in the real plane. So we'll review some basic operations with complex numbers. The first one is addition and subtraction. Addition and subtraction is just like if I were a variable. You're just going to add or subtract like terms. So in this case, I have -3 plus 4i plus 4 plus 5i. So if I want to add the -3 and the 4, I end up with 1, and I add the 4 and the 5, and that gives me 9i. So that's pretty simple. You just add like terms. Now, if I want to multiply complex numbers, you're going to treat the complex number like a binomial. And just remember, when you're multiplying I times I, when you're squaring I, that's equivalent to -1. So in this example, I have -2 plus 4i, and that whole thing is squared. I can write it twice and then multiply it out. All right, and now I multiply it just like I multiply binomials. The first, and then the inside terms, and the outside terms, and the final term. So I'm going to write it all out. So I have negative 2 times negative 2, plus the inside terms would be negative 2 times 4i. The outside terms would be another negative 2 times 4i. And then finally, 4i times 4i. You don't necessarily have to show that step if you know what to do, but I'm writing it all out for you. My eyes are looking really weird here. Okay, so this simplifies to 4 minus, this is an 8 and an 8, so minus 16i, plus what I get here is 16 times negative 1. So this ends up being negative 12 minus 16i. The only difference, you treat the i's like a variable, except you have to remember that when you square the imaginary number I, you get a negative 1. Finally, we're going to look at complex conjugates. Complex conjugates are when you have the same coefficients but opposite signs. And what happens when you multiply complex conjugates is it's a way to get rid of the imaginary part. Because if I were to multiply this out, I would have a squared, and then I would have a times bi, and negative a times bi, and then I would have the last term, which is b times negative b times I squared. So when you have that, you have a, and then these guys add to 0, and you're left with minus b squared, and then this is another negative 1 because I squared is negative 1, and that gives you a squared plus b squared when you're done. So complex conjugates are helpful when we have imaginary numbers in the denominator, because we always like to get rid of those. We like to have whole numbers in the denominator. So we'll work an example like that, and then we're going to practice more of this in class. All right, here's our example. This is division of complex numbers, where I have 4 minus 3i divided by 2 plus I. I'm not really going to divide necessarily, but what I am going to do is simplify this by applying the complex conjugate. If I look at the denominator, 2 plus I, its complex conjugate is going to be 2 minus I. So in order to multiply the denominator by that, I also have to multiply the numerator by that, because I'm multiplying by the equivalent of 1. And then this is just binomial multiplication. We're going to multiply it through and simplify, and when you're done, you should have a whole number in your denominator. So here we go. 4 times 2, if I do the top, I have 8. That's 4 times 2, and then the 4 times negative I, so that's minus 4i. And then negative 3i times 2, that's minus 6i. And then finally negative 3i times negative I, that's going to be a positive 3i squared, which turns it into negative minus 3, if I did that right. Yep, that's the numerator. And then the denominator, 2 squared is 4. 2 times negative I is minus 2i. I times 2 is plus 2i, so my imaginary numbers are going to add to 0, and then finally I times negative I is negative I squared, and that turns into positive 1. So to simplify, we end up with 8 minus 3 is 5 minus 10i all over 5, which reduces down more. Oh wait, so I can reduce the 5 and the 10 with the 5 in the denominator, and my final answer ends up being 1 minus 2i. So that's how you apply the complex conjugates to simplify division. And we will work on the rest of this in class.